Hello, everyone, and welcome to another wonderful day of chemistry. So it's time to talk about one of my favorite state functions, the Gibbs free energy. So last time we brought up how we could use the total entropy to figure out the favorability of a system. But in practice, we often have to constrain it. So if we constrain it with isochoric conditions, we produce the Helmholtz free energy, which is a favorite of engineers. But it turns out us chemists, we love isobaric or constant pressure conditions. So if we take our universal entropy, which again we can define based on the entropy of the system and the heat of the system, well, if I constrain this under isobaric conditions, I can go ahead and replace the heat with isobaric heat, which is just another way of saying enthalpy. So it turns out that we can determine the overall favorability based on the entropy of the system, the enthalpy of the system, and the temperature. Now, again, that universal entropy is A, little awkward mouthful, and also B, has weird units. So we're going to do the same thing we did with Helmholtz. We're going to multiply it by negative T. So if I multiply the isobaric universal entropy by negative T, I produce the Gibbs free energy. So this is the type of free energy we most encountered in general chemistry. And it can be defined based on the change. The change in Gibbs can be defined based on the change in enthalpy and the change in entropy. But it turns out it's often useful if we don't just look at the changes, but we actually also define the absolute Gibbs. So the absolute Gibbs free energy can be defined as the enthalpy minus the temperature times the entropy. Now, this also means that if we're looking at non-isothermal conditions, we can go ahead and figure out our general definition for the change in entropy by taking the derivative, or by the change in free energy, by taking the derivative of each component. So on the left, this is easy. It's just the change in Gibbs free energy is going to be related to the change in enthalpy. But it's also going to be related to the change in TS. Now, if I use my product rule, this is going to be the change in the entropy times the change in temperature minus the change in temperature times the change in entropy. Notice that if I'm looking at isothermal conditions, then this term would drop out. Otherwise, we get to keep it. So we'll be using both definitions, both the isothermal relationship and also the general relationship, because each will have kind of its place. Now, let's go ahead and try and do the same trick we did for last time. So now we have our general definition of the Gibbs free energy. Let's try and figure out what this means in terms of the physical meaning of the Gibbs free energy, just like we did for Helmholtz. Now we can go ahead and do this by putting in our definition for the enthalpy as just being the change in internal energy plus the change in PV together. Now, when we do this, we can also do the same trick we did for Helmholtz. We're going to insert in our first law. So the Gibbs is going to be the change in heat plus change in work plus PdV minus TS minus SdT. Notice this quickly got too long. And we can go ahead and do a more general derivation, but we're going to go ahead and simplify systems by making some approximations. So the first of which we're going to assume is isothermal conditions. So if I have isothermal conditions, I get to immediately drop out that dT term. Then we can also use the same tricks we used from Helmholtz and realize that TD minus TDS will cancel out with the TDS from heat. Because again, we can assume that reversible heat. Now what we're left with is just going to be the work, which again is going to be that reversible maximum work plus PDV. So we're just left with these two terms. Now we're going to separate that work into two components. This is the first time we're really going to go ahead and specifically address that the work we've mostly been looking at is the PV work. But we also have other kinds of work. So this will be electrical work, chemical work, reaction work, magnetic work, a whole bunch of different types of work. But we can also go ahead and split up that PV term, which will be PDV and VDP. Now, we're going to go ahead and assume that we're looking at isobaric conditions because we're already looking at Gibbs, so we've already kind of made that assumption. So this is a pretty robust term. Now, in that case, we get to immediately drop that dP term. Then we also notice that, hey, PV work is just minus PdV. So that is going to end up canceling out with my PdV. So these two end up canceling out. And all I'm left with is it turns out the Gibbs is related to the maximum non-PV work. Now, if I'm an engineer, the type of work I usually care about is going to be expansion compression because that's going to be most of my mechanical work. But as chemists, we often care about non-PV work because one of our favorite types of work is actually accomplishing chemical reactions. So if I want to figure out how much energy I can use to drive a chemical reaction or even generate electricity if you're an electrochemist, you don't care about the Helmholtz, you love the Gibbs because that tells me how much energy I can get out of a system in another case, specifically that reaction work. So we're often going to care about Gibbs when looking at reactions. So let's specifically kind of take a look at the Gibbs for reactions. So it turns out because Gibbs is based on the enthalpy, just like we can't find the true enthalpy of a system, we can't find the true Gibbs because there's too many types of energy embedded inside the system. So instead, we often need a good reference one. And the one most typically used is going to be the Gibbs of formation. Now, the major way we're going to find the Gibbs of formation is by taking the enthalpy of formation and subtracting out the entropy of formation. Notice, very important here, that this is not the entropy, it's going to be the entropy of formation. So you don't confuse the entropy of formation and the third law entropy. If you do, you'll get the wrong Gibbs. Now, again, the Gibbs is going to be referencing here, forming the chemical species of interest from its components in their elemental forms in their standard state. However, once we have this Gibbs of formation, we can usually find our Gibbs of reaction by taking the Gibbs of formation of the products and subtracting out the Gibbs of formation of the reactants. However, it is worth noting there's another common way of determining the Gibbs of reaction, and that's simply by saying, hey, I can just take the enthalpy of reaction and then subtract out the temperature times the entropy of reaction. So we've got two major ways to find Gibbs, and we'll use both fairly frequently, though oftentimes we're going to determine it from the reaction instead of the formation, but both are fairly common. So let's go ahead and do this as kind of an example. So let's look at a fun, good old organic reaction. The hydrogenation of acetylene. So this is going to be taking acetylene and adding hydrogen gas. So a nice gas phase reaction. So we get to use most of our ideal mechanics. So this will go ahead and produce ethane. Now we can figure out this in several different ways. So we can figure out our Gibbs energy of formation from our enthalpies and entropies of formation, already done here. And you can often find these Gibbs of formation in a table. So if I want to figure out the Gibbs of reaction, I can simply take the products minus the reactants, and then again, making sure to take account of stoichiometry. In this place, not a big deal because the formation of hydrogen is just 0. So if I do this, we figure out the Gibbs free energy of reaction is just negative 242 kilojoules per mole. So noticing this value is very negative, which means this reaction is incredibly favorable. But another way we can go ahead and determine this is by taking the Gibbs free energy of reaction, using the enthalpy of reaction, the entropy of reaction. So in this case, we can find the enthalpy and entropy of reaction by using the difference in their formations, like we saw earlier, both last chapter and this chapter. So when we do this, we'll find the enthalpy of formation is again negative 311 kilojoules, meaning that enthalpically this reaction is very favorable. And then the entropy here is going to be negative, meaning that this is a very unfavorable entropic reaction, which makes sense. I'm going from 3 reactants to 1. So we're highly ordering the systems. We go from a lot of gases to 1. Now, again, we add in the temperature, and when we do this, we find the overall Gibbs reaction is also negative 242. So notice both of these approaches should always give you the same answer. If they don't, always be kind of concerned. Most common failure here is that you went ahead and used the wrong entropies. So again, make sure if you're especially figuring out the Gibbs of formation, you're using the entropies of formation, not the third law entropies. Now, special consideration needs to be taken if we're looking at aqueous reactions, because the Gibbs energy of formation for ionic species is determined slightly differently. So for free energies of formation for an aqueous species, we go ahead and use them in reference to the aqueous to the collected aqueous species. And this can be determined in the usual way. If I'm looking at hydrofluoric acid, I determine this from hydrogen gas and fluorine gas, and I can get the Gibbs free energy of formation for the whole species. But if I care about the energy for the individual ion, what we do is saying that if I have an aqueous species, the free energy for its formation should be equal to the formation of both of the ions individually. The problem is that we know the energy of formation, but we now have two different things. So I usually have to arbitrarily set an ion to a known value. By convention, the ion we have a known value for is going to be the proton. It's the most common ion, so its free energy of formation is arbitrarily set to 0. This means that we're really doing everything with respect to how easy it is to get a proton at 1 molar. Notice this will be a pH of 0. So not necessarily very common, but makes a good reference point. Now, if the energy of formation for the proton is 0, that means the energy of formation for the other ion is going to be the same thing as the acid. So that means that if I'm usually going to be trying to figure out the energy of formation for an anion, I'm often going to go ahead and start by figuring out the energy of formation for its corresponding acid, because then those two will just be the same. The problem is if I'm looking at the energy of a cation, now I can't go ahead and arbitrarily note the other species because the other species won't be another cation. So by convention, you're usually going to first need to use a process like this to determine the free energy of an anion. Once you have that, you can determine the free energy for any other dissolved cation using the known anion. So let's say I'm interested in sodium. So I'm going to go ahead first start by looking at the free energy for sodium fluoride. Again, that way I already know the energy of the fluoride. I can figure out the sodium. So in this case, the free energy of formation for the aqueous sodium fluoride is going to be about negative 600 kilojoules. Then I know that the free energy for the sodium fluoride is going to be sodium plus fluoride. I already know the fluoride. That means I could rearrange it to solve for the sodium. It will be the combined ion minus the fluoride. And there you go. Plug in the numbers. You get your sodium. And then you can extrapolate this based on known formations of various solids to figure out any cation or anion of interest. So again, be a little cautious. So far, your Gen Chem knowledge should serve you fairly well for non-aqueous reactions, but for aqueous, keep an eye out for the fact that the formations for the aqueous ions mean something a little bit different. So next time, we're going to really be delving in how we can determine various free energies of reactions using thermodynamic cycles. Until then, take care.